Sagarika, kindly share your screen. We'll have 12 minutes plus 3 minutes for questions. 10 minutes, I will let you know. Okay, so let's start. Please go ahead.
Can you make it full screen, Sagarika?
Very good afternoon, everyone. Today I'm going to talk about the deviation.
We can't hear you.
We are not able to hear you.
Hello.
Sagarika, we are not able to hear you.
Is it audible now? Hello.
No.
Can't hear you at all. Maybe is Devabrata is ready. We can. Sagarika, we are not able to hear you for whatever reason.
Am I audible now?
No, not enough. What we can do is Devabrata ready?
Hi, sir. I am ready.
You're ready? Sagarika, if you stop sharing, you fix your audio. Okay, we'll come back to you in 10 minutes. After Devabrata stop. Okay,
Yeah.
maybe you can start sharing. It will throw Sagarika's screen out, Devabrata.
Let us stop the screen share. Okay.
Okay, let me just. Are you able to share? Oh, Sagarika has removed sharing the screen.
Yeah. Can you see now?
Yes, make it full screen.
Okay. Great.
Yeah, so sorry for that. So we'll start with Devabrata. Again, 12 plus 3. At 10 minutes, I will let you know. Please go ahead.
Okay. Hello, everybody. I am Devabrata Aduk, final year PhD student at IUCA. Today, I'll be talking about the fourth generation CMB space mission, ECO, and the challenges it is going to face that to detect the primordial P modes in the CMB. In this meeting, many people have talked about inflation, primordial gravitational wave, etc. I'll be talking about how we can detect that signal and what are the challenges we are going to face to detect the inflation. So, as you know, the CMB is the oldest and the cleanest cosmological probe of the universe, and the Planck mission has already extracted almost 100% information from the temperature map of the CMB. Only 10% of the CMB is polarized, and it contains a rich scientific information. One of the unsolved problem in the cosmology is whether the inflation is true scenario of exponential expansion of the early universe. There is no observational proof as of now, and if inflation is the true scenario of the exponential expansion, there must be a primordial gravitational wave which will imprint a primordial B mode signal in the CMB polarization. So here I have listed few future CMB probes which are targeting to detect this primordial B mode signal for tensor to scalar ratio of the order of 10 to the power minus 3. The CMB S4 and SO are the ground-based observations, and this light bird is the space-based observation. These three are underdeveloped, and there are two high-resolution CMB probes like PICO, which is in the NASA concept phase, and CMB Bharat is one of the proposed CMB mission on behalf of the Indian CMB community to the Indian Space Agency. Now, let me talk about the CMB Bharat consortium in brief. This CMB Bharat mission was inspired by the European Space Mission Core, the Cosmic Origin Explorer. However, that proposal didn't pass to the ESA because the main issue was the budget. The mission budget didn't fit their M-class envelope. So ESA encouraged European community to consider the large international partnership. and Indian responded in that. So in ISRO headquarters in January 2018, a formal consortium, the CMB Bharat consortium, was built up with 90 members from 15 different institutes. That consortium had submitted the proposal of fourth generation CMB space mission. The space mission name is the Exploring Cosmic History and Origin (ECO), although the mission is popularly known as the CMB Bharat. This will be the near ultimate polarization CMB mission. In this plot, I am comparing the noise level of the ECO, which is in the this orange line, with a Lightbird mission with the cyan curve and the Planck. So as you can see, the sensitivity of the ECO will be order of magnitude better than the Planck, and it will also be better than the Lightbird. Also, the resolution is quite good enough compared to the Lightbird mission. But major difficulties in detection of the primordial B mode is the foreground. In this plot, I am showing the primordial B mode power across the frequencies for 3 different tensor to scalar ratio, along with the dust and synchrotron, which are the 2 major foreground contaminations in primordial B mode detections. If we want to detect the primordial B mode, we need to understand these foregrounds quite well and subtract adequately from the CMB. Apart from these 2 major foregrounds, there are 2 other foregrounds like the spinning dust, which may be 1 to 2% polarized, and the point sources, which may be 1 to 4% polarized, that can also contribute in the foreground contaminations in CMB detections. Another challenge is the lensed B mode, which is generated from the E mode and shown in the green curve here, and that confuses the primordial B mode shown in the blue line here. And there is a class of technique called delensing, which reduces the power of the lensed B mode, shown in the dotted line, which helps to increase the detection sensitivity of tensor to scalar ratio measurement. Now, in our analysis, we mainly tested whether the ECO configuration, this is the mission configurations according to the CMB Bharat proposal, we have tested in our forecast study whether this instrument configuration is capable enough to reach the tensor to scalar ratio of the order of 10 to the power minus 3. Here we consider many different foreground models. Mainly for the dust, we have considered 3 dust models, where the simple dust model with the G-Nilk dust, and 2 main dust model which considers the depolarization. Depolarization in simple language is the dust polarization angle is different at different frequencies. And we translate this model with modified black body because dust follows the modified black body at microwave bands. And also we consider the synchrotron and use 3 scaling features, the power law models, curved power law model and Galprop model, to translate the synchrotron template to the microwave bands. We also consider the spinning dust and the point sources. Based on these dust and synchrotron complexities and others 2 foregrounds, we simulate 11 set of simulations where we consider the different combinations of these foreground models, along with the fully lensed CMB as well as the 84% delensed CMB map. Then we pass all those simulated sky map, the total sky map, in 2 foreground component separation technique. The foreground component separation are the techniques to separate the CMB from the foregrounds, where we consider the needlet ILC, one blind component separation method, which doesn't assume anything about the foreground model, and the commander, which assumes different models of the foreground and feed those models across the frequencies and extract the CMB out of the total frequency maps. Then from this clean CMB, we compute the power spectrum, the total power spectrum, and that power spectrum has been fitted by the model to infer the tensor to scalar ratio R. In this table, I have summarized the main results for all set of simulations. In first simulation, we consider only dust and synchrotron, and one by one we added the 2 other components. Since these 2 components mainly contaminates the small scale, it doesn't have much impact on tensor to scalar ratio measurement. And when we reduce the lensed B mode power by 84%, we have seen that detection sensitivity increases around 55%. And then these 2 simulations, we consider the 2 synchrotron scaling, the power law and curved power law. And I'll come to this point why this bias is quite large. And most importantly, where I want to draw your attention to is the decorrelated dust. I have emphasized here. So decorrelated dust cannot be mitigated using the existing component separation technique. As you can see, this bias and uncertainties are quite large because the contaminations remains in the clean CMB map, and that is effectively producing the larger bias in tensor to scalar ratio. In this plot, I am comparing whether forecasted tensor to scalar ratio are consistent with the null detection, which is shown in the vertical dotted line at 0. And as you can see, most of the foreground complexities are producing the foreground residual bias, which are consistent with the null detection within 2 sigma or 3 sigma level. Only one foreground configuration where we considered the this curved parallel synchrotron. Curved parallel synchrotron cannot be mitigated using the commander technique because we do not have many frequency channels at low frequency end of the spectrum where the synchrotron is the dominant. And that's why this so in this plot we are showing the synchrotron spectral index distribution. The green is showing the commander recovered, and green is showing the input, and the blue is showing the what commander had recovered. As you can see, this distribution are quite different. That's why the synchrotron cannot be mitigated using this very small number of channels at low frequency ends, and it produces the immense bias. Like it's not consistent with the 3 sigma with the null detection as well at all. Also, another point, the decorrelated dust, which cannot be mitigated neither using the commander nor using the. Sorry.
10 minutes.
Okay, sure. So and then I have tested on the other tensor to scalar ratio which are non-zero, ranging from like 10 to the power minus 3 to 10 to the power minus 2, and this shaded line basically is showing the 1 sigma region where you consider the length CMB, and the 84% delensed CMB means the 84% lensed power has been reduced. As you can see, this this magenta curve is like almost 55% larger width than the this orange line. That means 84% delensed CMB can increase the detection significance around twice, which is quite evident in this plot. Here I am showing the detection significance for this tensor to scalar ratio. For 10 to the power minus 3 can be detected with 84% delensing by like 5 sigma, and 10 to the power minus 2 can be detected almost 24 sigma. So this was all the forecast results we have produced for this CMB mission. Let me summarize the talk. So ECO is a very efficient full sky CMB near ultimate CMB polarization mission, which will operate at high resolution, and it has a quite large frequency band ranging from gigahertz to terahertz band, and it has a huge discovery space ranging from inflation to particle physics, extragalactic astronomy, many things. And one main target was to detect tensor to scalar ratio of the order of 10 to the power minus 3, which can be achieved for a simple foreground model. But if the foreground is quite different than what we understand the foreground is, that can create an immense bias. And for to mitigate that types of foreground, we need to build a new component separation technique. The CMB Bharat is still alive in the ISRO OOMP, and we need to trigger to make this mission successful. Thank you.
Thanks, Devabrata, for the nice talk. We have time for a couple of questions. Sriram.
Hi, thank you, Devabrata, for a nice talk. What is the biggest challenge in terms of the foreground?
Yeah, so biggest challenge is, so in this paper, we try to test whether the existing component, the foreground cleaning method are sufficient enough for this high sensitive instrument. We have seen as the Planck has reported at 2017 paper, the dust is decorrelated, means you cannot use one template at one frequency and translate it simply by modified blackboard. It's not true. So that types of complexity cannot be handled for this high sensitive instrument using the existing components representing.
I understand. So can you go to that slide where you had the sensitivity or the foreground as a function of frequency very early?
Here, yeah.
Right. Finally, so do we understand the foreground with respect to, dust better or synchrotron better? Because we need to decide at some point, whether how high the frequency we need to go to, etc.
Yeah, so the two components are dominant at two different regime of the frequency bands. The synchrotron is the low frequency band and the dust is the high frequency band. We need to understand both, in reasonable accuracy. Because where the CMB is dominance is like from 100 to 270, but the synchrotron is a dominant foreground. So we need to consider that frequency bands where the synchrotron must be mitigated. So we need to understand both the dust and synchrotron.
I understand. Can you go to the next slide if you don't mind? I believe it is what is that line on top of the green that you have? Yeah. Yes.
I'm not sure, but I think this is the data of the lensed B.
Okay. I understand. Thank you.
Okay, so there are no more questions. I can ask one very quick question. So you have said that you use a gray body for your dust model, right? So
right.
What kind of temperatures do you put for that, or are you able to constrain the temperatures?
No, so we simply had borrowed the Planck results. It's the temperature is like 19.6 Kelvin, and the spectral index like minus 1.5, something like that.
Okay, but that number is, can you constrain that number, or because if I understand, that is something you have to assume, right?
That is something to assume, but that is reasonably well constrained by the Planck mission. It may vary in the 3D ISM, which we do not understand. How the ISM behaves in the 3D, neither we have data nor we have any analysis. So it may vary, but it's like a mean temperature on the 2D, based on the 2D analysis.
Okay, so let's thank Deviations again.
Thank you.
You can unshare your screen, and Sagarika, you can share your screen again.
Am I audible?
You are still not, you're faint.
She has fixed the, can you share your screen, Sagarika?
Yes, but am I audible now?
But we can't hear you.
Okay, I shall unmute myself from other device. So is it audible now?
Yes. Yeah, better. Maybe you need to, if you're using a headset or something, please speak closer to the microphone. This is better.
Okay.
Speak loudly and closer to the microphone and start sharing your screen.
Yes. Very good afternoon, everyone. Today I'm going to talk about deviation from slow roll inflation and its implications for magnetogenesis. So this talk is based on our recent work with Professor L. Shram Kumar, Dr. Rajiv Jain, and Dr. Devika Chaudhary. The archive identifier is as follows. The outline of my talk goes as follows. First, I will start by talking about the generation of the primordial magnetic field and the electromagnetic power spectra. Then I will talk about the choice of coupling function for slow roll inflationary models. Then I will talk about the construction of coupling function for models generating features in scalar power spectrum. Under this, I'll discuss two types of models, one that generate features over large scales and others that generate features over small scales. Then I will conclude the talk with the summary. So as it has already been discussed by Professor Kandu and Dr. Rajiv Jain in details about the observational evidences of the magnetic field, I will not go in details. I will just quote the numbers. In galaxies, the magnetic field of strength 10⁻⁶ Gauss is observed on scales 1 to 10 kiloparsec, while in cluster of galaxies, the strength is of the order of 10 power minus 7 to 10 power minus 6 cos on scales of 10 kiloparsec to 1 megaparsec. The intergalactic medium void magnetic field strength has a lower bound of 10 power minus 16 cos on scales above 1 megaparsec. So these magnetic fields are the amplification of the pre-existing seed magnetic field by dynamo mechanism, and the origin of these seed fields can be assigned to the processes during inflation of the early universe. Now, let's see the generation of primordial magnetic fields. So we know that the standard electromagnetic action is conformally invariant. So to generate the magnetic field that gives us the large-scale magnetic fields today, we need to break the conformal invariance. And for that, we have introduced a coupling term that couples the electromagnetic field with the inflaton field. So the corresponding Mukhanov-Sasaki equation is given by this equation, and the power spectrum looks like this. So now let's see what kind of coupling functions we can work with. So we have worked with a coupling function which goes as power law of the scale factor. So n is the power of a, and for this coupling function we get a spectral, the magnetic field spectral index looks like this, and the electric field spectral index looks as this. So we have worked with the case n equal to 2, that the magnetic field gives us a scale invariant power spectrum which has this form, and the electric field power spectrum goes as k square. We have written the magnetic field spectrum and the electric field spectrum in terms of parameters R, which is the tensor to scalar ratio, and AS is the amplitude of the scalar power spectrum. Next, we will move on to the helical magnetic field. Here we have added a parity violating term to the action I have discussed earlier. Now we have worked with a simple case where J is equal to I, and here gamma is the helicity parameter. So what we have done here is the equation of motion for the for this action, and sigma plus and minus 1 represent the positive and negative helicity. So the expression of the electric and magnetic power spectra has this form. So now for this also we have obtained scale invariance for n equal to 2 case. Here, as you can see, PV is the magnetic power spectra, which is nothing but a factor of F gamma times the magnetic field power spectra for the non-helical case. And this is the expression for the electric power spectra for the helical case. So for gamma equal to 0, that is when we turn off the helicity, we can recover the magnetic and electric power spectra for the non-helical case. And we have worked with the case gamma equal to 1, where F gamma is equal to 10 power is of the order of 10 power 3. And as you can see here, we evaluated the power spectrum at the end of inflation. And for gamma equal to 1 at the end of inflation, when these two terms vanish, we can see that the expression of PB and PE matches. So next we will see the coupling function and the power spectrum for the slow roll models. So in slow roll inflation, for inflation driven by a scalar field, we know this is the Klein-Gordon equation.
Hello, Sagarika, can you hear us? Sagarika, Nishikant, can you hear me?
Yes, I can hear you. Sagarika, we cannot hear you. Sagarika, we still cannot hear you.
There's problem. Okay, she has got disconnected. We'll just wait for her.
She's at IIT Sriram.
Yeah, she's on campus. She's speaking from the office. I don't know whether there is a, well,
Dawood also had some issues. Right?
sorry?
Dawood also had some issues.
Yeah, it shouldn't happen. Just let me just check. Give a minute, Nishikant, please bear with me.
Yeah.
Let's see.
Hello.
Sagarika, are you able to hear us?
Yes, I can.
Your voice is again very low. What had happened? Anyway,
I don't know. There is some network fluctuation. I don't understand.
that is okay. Can I just share the screen, speak closer to the microphone and continue from where you left off?
Yes. Sorry.
Yeah, it's okay. Just if you're, can
You probably
you
have
make it full screen?
Am I audible now?
No, you have two devices close by and it is feeding back.
Is
Can
it
you just
fine
make
now?
it full screen and speak loudly?
Yeah, is it audible now?
Yes, it is okay, I believe. You proceed, please. Make it full screen and proceed.
Yes. So as I was saying, that the we cannot use a specific form of the coupling function J of phi as here we can see that the evolution of the inflaton field depends on the potential of the model of interest. So a specific form of J of phi will not give us this form of J of n, which is we are emphasizing on this form of J of n because we already saw that this form leads us to a scale invariant behavior of the magnetic power spectrum. So now we have constructed different coupling function for different models. So first model we have considered is the quadratic potential. Here we have substituted this V of phi in this equation, and in the slow roll approximation we have evaluated the phi of n, and we have constructed this G of phi in such a fashion that it will give us a scale invariant behavior, and it will lead us to this form of J of n. So there are two other models we have discussed in our paper. One is the small field model, whose potential has this form. And again, by using the similar method, we have constructed a coupling function for this model. And the next model of interest was the Starobinsky model, whose potential has this form, and the coupling function looks like this. So now for these models, as the way we have constructed the coupling function, as predicted, it has led us to a nearly scale invariant behavior in the magnetic power spectra and a k-square behavior for the electric power spectra. As you can see here, that here the dashed lines are the helical case and the solid lines are the non-helical case. As I have mentioned earlier, there is a 10^3 gap between the non-helical and helical amplitude, which we obtained as predicted. And we get a nearly scale invariant behavior for the power spectra of for both magnetic field for both helical and non-helical case, and the amplitudes of electric and magnetic power spectra matches for the helical case. Now that we have discussed the slow roll models of inflation, next we will talk about the models that involve deviation from slow roll inflation, which leads to generation of features in the scalar power spectrum. So these models that generate features over large scales, we have taken a bunch of models into consideration. One where we can introduce a step by hand in the slow roll potentials I just discussed. This is the form of the step we have introduced to the potential. So here alpha is the height of the step, del phi is the width, and phi naught is the location of the step. So the magnetic power spectrum, we have recovered, we have obtained a similar power spectrum as before, other than there is a step-like feature due to the introduction of this step in the potential. And otherwise, this is nearly scale invariant throughout. And similarly, the electric power spectrum also showed the same behavior, other than there is a step-like feature here. Next, I will discuss a different model where we have a change in slope in the potential. This is the Starobinsky model. This is another Starobinsky model, which consists of a linear potential with a sharp change in slope in between at the position phi naught. So as you can see, there are two slow roll regions, and due to this sharp change in slope, there is a deviation from slow roll that occurs. So for numerical analysis, we have smoothened out the potential because of this sharp change by introducing a step function of this form. So now how we have constructed the coupling function for this potential is, first we have, like we have done in the case of the slow roll models, as I have explained earlier, we have solved the background equation for the inflaton field in the first slow roll region, and we have constructed a coupling function using that solution. So what we observe it, because of the behavior we are trying to achieve, that is the a square behavior of J, what we obtain that we get a scale invariance for the modes that exit the Hubble radius in the first slow roll region, but there is a strong blue tilt for the modes that exit later.
10
Similarly,
minutes.
yes, hello,
2 more minutes, Sagarika.
2 minutes. Okay, I will try to wrap. Similarly, for the if we use the solution of the field in the second slow roll region, we got a strong red tilt for the mode that exited earlier, while there is a scale invariance for the for the modes that exited in the second slow roll region. So to avoid these strong features in the power spectrum, we tried to combine both the solution of phi in both the regions, and we managed to get a scale invariant behavior for both the large and small scales here, with a burst of oscillation in the middle. That is, we called it that we have ironed out the features by introducing a step-like function between the two coupling functions, and we obtain the desired strength of the magnetic field and a k-square behavior for the electric field. Now, the third type of potential, Nilanjan has just discussed that the potential that generate primordial black holes and secondary gravity waves. So this is the kind of potential with the inflection point in the potential. So how we have chosen the coupling function for these type of potential is, since the field slowly rolls down the potential in the initial slow roll region and then gets stuck or hardly evolves once it approaches the inflection point, so it is analytically difficult to get a solution for phi for these kind of potentials. So what we have done is we have solved the background equation numerically for this, and we have fitted the inverse function n of phi with different polynomials for different models that involves inflection point, because there is a brief departure from ultra slow roll where the field gets stuck. So we had to adapt to this method because we don't know the solutions. So now that we have done the fitting of n of phi with different polynomials, we have used that n of phi to construct a j of phi, which will give us a scale invariant spectrum, at least in the slow roll region. So here we have, for this potential, we have fitted with a second order quadratic polynomial with the n of phi and constructed this coupling function. So the next two models are the models that generate features over small scales that we just saw in the previous talk, that generates enhances the power in small scales. So for ultra slow roll model, we have constructed a coupling function by fitting the phi 4 polynomial, and for the second punctuated inflation model, we have fitted with the phi 6 polynomial. So this is how the J looks like. This is the first slow roll parameter for each model, and we can see here that once the field approaches the inflection point, there is a drop in the first slow roll parameter, and J almost becomes constant. For this kind of behavior and construction of J of phi, the power spectrum has this behavior, where you can see that we obtain a scale invariance in the initial slow roll region because we have constructed the J of phi in such a fashion, and because J becomes constant once the ultra slow roll sets in, we get a k power 4 behavior for the modes that exit the Hubble radius later. Similarly, this is for the models that generate for the first punctuated inflation model that generated feature in large scales.
You should wind up soon, Sagarika.
Sorry?
Wind up in a minute or so.
Yes, sir, I'm done. This is the power spectrum for the models that generate feature over small scales. As you can see here, we obtain scale invariance for the modes that exit in the initial slow roll region. And again, there is a k power behavior, which accounts the J equal to constant behavior. And as you can see here, we got a k square behavior for the electric field non-helical case, and there is a gap of 10 power 3 between the helical and non-helical case, and the amplitudes of the helical electric and magnetic fields also matches. So yes, so to conclude, we had faced challenges in constructing these coupling functions because although we get a scale invariance in the slow roll region, but the magnet strength of the magnetic field is suppressed largely for large scales. And for the Starominsky model, where we have tried to iron out the features, we had to do a lot of fine tuning. So although these models we can take into consideration that has implications in improving fit to the CMB data or the generation of PBH and secondary gravity waves, but these models pose a lot of challenges in constructing the coupling function and hence the generation of primordial magnetic fields. Thank you.
Okay, let's thank Sagarika for a nice talk. So we can take a couple of questions. Okay, Kandu.
Hi, Sagarika. Interesting talk and interesting work. So, is your conclusion? So, which one would you like to rule out? Those modifications to the potential, or that magnetic field cannot be generated?
If we can adopt some method where we can iron out those strong features, so that K power 4 behavior that we are getting. See, as I explained in the Starobinsky model, although it needed a lot of fine tuning, but we got a spectrum which is of the desired strength and it's really scale invariant. Similarly, for the other models, if we can somehow straighten out that K power 4 behavior, we can expect that they also can give us a desired strength of magnetic field, which can lead to a detectable strength field.
Yeah, one thing which I would comment is that there is nothing sacred about scale invariant spectrum. Of course, if it's k to the power 4, then you have to stop it somewhere. So otherwise things will blow up. So either you can stop it by ending inflation or something like that. So I personally don't think there is something very sacred about maintaining a scale invariant spectrum. So maybe that's just a comment.
We can't hear you, Sagarika.
Don't we need a scale? Am I audible?
Yes.
Yeah, now.
Don't we need a scale invariance because otherwise the field will decay as 1 by a square, and during inflation it goes as exponential n. So if we don't go for a scale invariant behavior, won't we lose all the magnetic field during inflation?
No, I mean, many people, including Rajiv or our papers, don't finally get scale invariant spectrum. And the only problem is it's not scale invariant. Either things will blow up at the infrared end or the ultraviolet end. So you have to regulate things at the beginning of inflation or at the end of inflation.
Kandu, the point is not about being strict scale invariance. The point is that if the moment you have any such ultra slow roll regime, you end up with extremely small amplitude on large scales. It's not just the K power 4. Probably the plots were not large enough for you to see the numbers.
Right.
What happens is that the moment you hit a epoch of ultra slow roll, on large scales, your strength of the magnetic fields are completely suppressed.
Correct. But on what scales are they not suppressed? I mean,
you can see, right, close to the end of inflation, 10 power 13 megaparsec inverse or larger, depending on where you want your power for PBH production, for instance. Or if you try to suppress power to improve the fit to the quadrupole and so on, again you hit a problem like this. Maybe we can discuss offline, Kandu. We are hoping up very much.
Okay. Yeah, it's a good thing that at least you're trying to come from the potential itself and some coupling function which depends on potential rather than just putting arbitrary functions of the scale factor. So that is always a nice thing.
Yeah,
Not
see,
I haven't seen any else do that.
yeah, Nilanjan wants to ask a question, maybe briefly, Nilanjan, or we can stop the recording and you can discuss with Sagarika.
Yeah, I have actually very short question.
Sure.
So Sagarika, as I understand, you will have the amplification in the scalar perturbation also. Are you considering the primordial black hole formation for this model?
Sorry, can you repeat?
Are you considering the prime of PBH for these cases?
No.
Okay. Okay,
Did I get the question? Like you're asking if you're, I can't hear the question. If you can just.
So, Nilanjan, the PBH formation have been, for these specific cases, have been studied elsewhere.
Oh, okay. I see.
So we are focusing on models which do indeed do that. Okay.
Okay, but if you consider the PBH formation, that will constrain the parameter space also.
Yes, we work in that parameter space.
Yeah,
Oh,
we
okay.
work with the parameters that has been constrained by the PBH model.
Okay. Now I understand. Thanks.
Yeah, Nishi, I think we should wind up.
Okay, so let's thank Sagarika again, and